My concept of now, which is at the heart of shape dynamics and the way we reinterpret Einstein's theory, is actually going against a really sacred cow. Now, Einstein abolished simultaneity. So you talk to almost any theoretical physicist and they say that simultaneity has no meaning at all. That's absolutely certain. They look very oddly at me when I question that. And it's perfectly true that in the special theory of relativity, there is no way that you can distinguish one now and say, for example, now here is the same as the now in the Andromeda Nebula. That's not possible. That's because actually the special theory of relativity has actually got a rather dull mathematical structure. There's no dynamics of geometry in it. Now, when you come to general relativity, there's no question that Einstein found it, a great help in finding it was the notion of space-time and the idea that there was no unique definition of simultaneity. But general relativity has a very special mathematical structure. And if you say that, first of all, time does not exist as some substance, and much more significantly, if you say that distance is not even, or size is not even really there, and I can perhaps say a little bit more about that afterwards, but if you say that, and then say, how can I represent the essential irreducible core of general relativity, then lo and behold, it turns out that there is a unique way to define simultaneity within general relativity. It's sitting right at the heart of the mathematics of general relativity, and it's closely related to soap bubbles, which is rather nice. In three-dimensional space, you can blow a soap bubble, and it has this beautiful, perfectly spherical shape. The curvature, it's what's called the extrinsic curvature. The way the soap bubble is curved in the embedding three-dimensional space, it's exactly the same everywhere you go. If you just looked at that way it's curved, the way it's embedded in space, you couldn't distinguish any point on the surface. It's exactly the same. Now, in four-dimensional space-time, there is something exactly similar. It's really soap bubbles in four-dimensional space-time. And these are the surfaces, the distinguished surfaces of simultaneity. And on these, the universe has a particular shape. So these are my shapes of the universe at a given instant. So this is actually sitting within general relativity. And the fact that it is there and that they play a special role has been known now for over 40 years. In fact, the man who was most responsible for it, his PhD student at the time was an Irishman called Neil O'Murchu, who was my collaborator 15 years ago when I started these ideas of shape dynamics and contributed very significantly to it. In fact, he is actually a major contributor to the present structure that the theory has. So it is sitting inside the mathematics of general relativity. But it gets very little, this work gets very little prominence, although it is very important. In fact, all of the numerical calculation, now there's a big field now called numerical relativity, and all of that could not be done at all without this work that was done by this man called Jimmy York, just a bit over 40 years ago, and his student Neil O'Murchu. And for some reason, I suppose it's the magic. You see, space-time seems such a beautiful concept, and it is a very beautiful concept. Pretty well every representation of general relativity talks about space-time. That's the first thing they introduce. All the students have to learn about it. But how general relativity works as a dynamical theory very seldom gets much prominence in the account. There's one very standard book by a very good relativist, Robert Wald, at the University of Chicago. It's a very good book, but that key part that relates to this work that was done over 40 years ago is put as the last appendix at the end of the book, Appendix C. He said, this is important, but it isn't really essential for the whole of the rest of the book. But actually, it does actually give the key to really what is going on in general relativity.